All right, moving onward to Chapter 18. Chapter 18 is focused on the refraction of light. Chapter 17, we spent a lot of time on reflection and mirrors. Chapter 18, we're going to spend time on refraction and lenses. So a couple things about refraction. Well, in general, what is refraction? It is the bending of light. So it is when light bends, and it usually occurs when we go from one medium to another. So if we take a look at the example down below, we have light going essentially from air to water. What happens? The light obviously bends. If you've ever been spearfishing or anything like that and you look into water, they always tell you when you're spearfishing and the fish is on the surface and you can see it, you're supposed to aim, I can't remember which one, above or below the actual fish, because the light refracts and makes it look higher or lower than what it actually is. So in general, refraction is the bending of light between two mediums when it crosses over from one medium to another. Now, a couple things when we talk about Snell's refraction, we have to deal with Snell's law of refraction. Just like reflection, where reflection was the angle of incidence equals the angle of reflection, we are going to be dealing with the angle of incidence and the angle of refraction, but they are not equal to one another like they were when we were dealing with reflection. So the angle of refraction is n. N is equal to the angle of sine of incidence over the sine of refraction. This depends on a substance. Every substance has a different n value. All these n values are constants, and they are in your book on page 486. Air is very close to 1, and then other materials are slightly above 1. It's very accurate and precise. You'll notice that this chart goes out 3-4 decimal places depending on the substance. So we are going to use the index of refraction, n, varying upon each substance, and solve for Snell's law of refraction. And Snell's law of refraction is n1 times the sine of theta 1 is equal to n2 times the sine of theta 2. So the Snell's law of refraction is going to help calculate the angle at which light refracts in a particular substance. Now, when we talk about the wave model of refraction, after talking about Snell's law, the wave model, light travels as a wave, fastest in a vacuum, as we talked about, approaching 3.00 times 10 to the 8th. We can help calculate n, or the velocity, in another medium by using n. So we're going to use n, the index of refraction, again. And how that's calculated, n is equal to c divided by v. C is the speed of light in a vacuum. V is the speed of light in that particular medium. So that is how n is calculated. So you may be able to calculate the velocity of light in a particular medium, or calculate n if you're given vice versa. So n is equal to c divided by v, the two kind of equations that we're dealing with for refraction, that n is equal to c divided by v, and Snell's law of refraction. So if we take a real life example of Snell's law of refraction, a light beam in air hits a sheet of crown glass at an angle of 30 degrees. At what angle is the light beam refracted? Well, what we have here is very simple. We have angle 1 in air is 30 degrees. N1, according to page 486, the n of air, the index of refraction, is 1.00003. We're trying to solve for angle 2, and we know that the index of refraction for crown glass, again looking on page 486, is 0.152. So if we go ahead and set up this equation, what we're left with is n1 times the sine of theta 1 is equal to n2 times the sine of theta 2. We're really just going to plug and chug. 1.003 times the sine of 30 degrees is equal to 1.52 times the sine of theta 2. Now, one thing for you trig and calc students, make sure that you are working in degrees, not radians. Make sure you're plugged into degrees. You're going to go ahead and solve for this. You're going to divide by 1.2, and you're going to find out that angle 2 is 19.2 degrees. Again, make sure that you are working in degrees, not radians. So there's the equation for refraction. Couple odds and ends that we got to clean up for refraction. Is total internal reflection. And you're probably thinking, why are we talking about reflection when we're dealing with refraction? Well, the two can kind of be related. And ladies, you're going to be really interested in total internal reflection sometime in your life, right before you get engaged, because you're going to want the highest total internal reflection in that diamond as possible to make it sparkle as bright as possible. So what is total internal reflection? The angle of reflection is greater than the angle of incidence when light passes into a medium of a lower index of refraction, so a thicker object. Two things come into play here. We have the critical angle, and that is when the refracted light lies between the two boundaries. So hypothetically, let's say I have my boundaries here. I have my green incoming light wave, and instead of being refracted through like we've talked about and changing the angle, what happens is it's refracted, but it's refracted right along the surface. That critical angle, this is the critical angle at which that refraction happens along the two boundaries. Now, when we talk about total internal reflection, it still deals with refraction, but this should give you kind of an idea. This picture should give you an idea. Occurs when light traveling from a region of a higher index to a lower index of refraction. That's the first stipulation. We have to be traveling from a higher index to a lower index. All of the light reflects back into the incident region. So what we have here is, we have 4 examples on the bottom, each angle varying. And what you can see here is in the blue we have the refraction angle, and in the green we have the reflection angle. Well, what happens is, now, if that angle becomes greater and greater and greater, what happens is we have no refraction at all and all reflection, and that's how we get total internal reflection. As you see, as we go here, as we go down from 0 to 30 degrees, our refraction angle is 42. At 60 or 45 degrees, our refraction angle is 70. At 60 degrees, we have no refraction angle, all reflection. And that is total internal reflection. And that's kind of the principle of light getting trapped in an object, such as a diamond, kind of works. It's that total internal reflection and the idea of how that works. Last thing, when we talk about refraction leftovers, all right, you're driving down the highway on a hot summer day, all of a sudden the road appears to be one big pool of water half a mile down. That's a mirage. How does a mirage work? Due to heat in the index of refraction. The air closer to the road is warmer than that above it, and it's slightly changing it. It's slightly bending it. Dispersion of light is when white light gets separated into a spectrum, such as through small prisms, such as little drops of water in the air. Just an example of how a prism. So that's dispersion of light. That's a rainbow. So mirages and rainbows all have to do with refraction, how light bends when it encounters a different medium, such as air to water, or anything else. The table of the index of refraction, which you'll have to use, is on page 486. And other than that, you'll have some questions in class tomorrow.